Hello, in this video we will talk about components and unit vectors. I'm trying this new background, which I think I like more because it's easier on my eyes. So when you want to add vectors, sometimes the graphical method is not the best, especially if you want higher accuracy. So in this video, I will remind you of the use of projections. We can project the vector parallel to the coordinate axis, right? These are called components. So let's define a vector. Here, I want to put an x-axis and a y-axis, and then let's go with something, let's say red. So I want to define the vector here, vector A, which is going to have a magnitude like this, and then it's going to have an angle. So the projection or the components of vector A are defined as follows. To project the vector parallel to the x-axis, like so, and this is going to be my x component of the vector A, and then we will also have a vertical component, which is parallel to the y-axis, which I'm going to call AY, and this is also a vector. So you see, this is a vector AX, this is a vector AY. Unlike all good vectors, I can, if I add AX vector plus AY vector, I'm going to get a third vector, which is my vector A. So I can write either vector A or I can write the components of vector A, and they are the same. Of course, using a little bit of trigonometry, we know that AX, the magnitude of AX, I don't put in the arrow on top, just the magnitude is the magnitude of A cosine of theta, while AY is the magnitude of A sine of theta. Don't memorize this. These equations are only good when the angle is parallel to, well, is measured from the x-axis, right? If they give you theta like this, let's say this is theta prime, then this doesn't work. As you can see, theta prime will be here, and then they have to be reversed. AX will be A sine of theta prime, and AY will be A cosine of theta prime. So just be very careful with that. I'm going to erase this, and then we can continue. So the same vector A can be expressed with components AX, AY in this way, or also in this way. This is another way to represent the vector when you decompose it. Okay, it's similar. So you can see it like this, or you can see it like this, and they are equivalent. So if you get the vector A in terms of the magnitude and the direction, you can find the components using this. But if you get the components first, right, you know what AX is and what AY is, you can always go back, just like we did before, and use a little bit of Pythagoras here, and then find the magnitude of your vector, and then find the angle of your vector, right? Which is the same thing we did in the last video. So remember that the angle is always, we need a reference. So the angle is always measured with respect to x, positive x. So if you have your vector, if your vector lives in the first quadrant like this, well, you're going to have an AX that is positive and an AY that is positive. If your vector lives in the second quadrant, then AX will be negative, while AY is still positive, If your vector lives in the third quadrant, well, you know, negative ax, negative ay. Finally, in the fourth quadrant, you have positive ax, negative ay. So you have to be careful when using sine, arcsine, arccosine, and arctangent, because calculators usually just give you the positive version of the angle. It's very important you realize in which quadrant you are working to get the right answer. So for example, if we have vector A, which is 30 meters at 140 degrees. So if we plot that thing, we see immediately that we are in the second quadrant, right? This here is 140. This here is 30 meters. Now, of course, this here is 40 degrees. So 140 plus 40 is 180. When you generate the components, you're going to have this component here and this component here. Ay, no problem, is positive. Ax is negative. So you can write Ay as 30 sine of 140 degrees, but you can write Ax as 30 cosine of 140 degrees, which will automatically give you the negative ax. And you can also say is negative 30 cosine of 40 degrees. So here you have two options. I'm not going to tell you which option you have to choose, just you do you, but I want you to remember that you have the possibility of using two types of notation. This gives you more control than this one. I prefer using this usually. Something else very important that I want to mention in this video is the notion of a unit vector, which we are going to use a lot this semester. A unit vector is a dimensionless vector that has a magnitude of exactly 1 and are specifically given a direction parallel to the x, y, or the z axis. So no dimension, magnitude equal to 1, and is parallel to a specific direction. So I'm going to define the vector I, the vector j, and the vector k. Vector I has a magnitude of 1 in the direction 0 degrees parallel to the x-axis. Vector j has a magnitude of 1 at 90 degrees with respect to the x-axis, which means parallel to y, and vector k has a magnitude of 1 at 0 degrees but with respect to the z-axis. Let me show you. So x, y, and z. You see, I has a magnitude of 1 parallel to x, j is parallel to y, and k is parallel to z. Why do we need these vectors? We use them as a bookkeeper. They're just a tag we'll assign to a scalar to remind us that this is a vector. Or actually, we're going to create a vector with a scalar and a unit vector. Let me show you how. Let's go back to our vector A in a plane, which we decompose in x and y. So I can write vector ax as magnitude of vector x. You see, I didn't put the line anymore. And I can say this in the I direction. Right? There you go. So these two notations are equivalent. Similarly, I can say that vector ay is equal to the magnitude of vector ay in the direction of the j unit vector. So one way to represent the decomposition of vector A will be ax plus ay vector vector, but we can also say that vector A is AXI plus AYJ. Make sure you understand the difference between these two. It's the same vector, but here we are using a scalar times unit vector plus another scalar times a unit vector. So let's see how we can use this new knowledge of unit vectors to our advantage. Let's say you have to add A plus B. So of course we add A, that will be our vector. Let me give it a little bit more of a slope. Let's say vector A and then vector B. So this is A and this will be vector B. Okay. We know well now that our vector C will be this. That's if we do it graphically. So, of course, if we decompose each vector, so we know that A plus B is equal to C. But if we decompose each vector in X and Y, this here, that's AX. This here, that's BX. And then this here, which I don't know, I'm gonna have to use another color. What is it here? This here, that will be CX. Similarly, here, this will be AY. They're all vectors, so I forgot. I want to put the little thingy. BY, and then all of this will be CY. So all vectors, okay? All vectors. You see how CX, at least the magnitude of CX, well, actually the vector CX will be AX, will be AX plus BX. Similarly, CY will be AY plus BY. In other words, if I add AX, which is this, plus BX, which is here, we get CX. And if I add this little AY plus this big Y, I get the whole CY. So I can re-express this as AXI plus BXI, and I can re-express the addition of vectors in Y as AYJ plus BYJ. And what this gives us is that vector C will be, if I rearrange everything, it's AX plus BX in the I direction plus AY plus BY in the J direction. You remember that when adding vectors is not easy, you have to do trigonometry, you have to use rulers and whatever. But if you use a decomposition of a vector, at one point what you do is an algebraic sum. AX and BX are not vectors, these are scalars. Similarly, AY and BY. So in this way, you can add scalars to add vectors. This also has the incredible power that if you ever encounter a vector A that has components, let's say 3i plus 4j minus 4k, because it's a vector in 3 dimensions, and your vector B is 7i plus 4j plus 2k, then you add them, you just do algebra, 10i plus 8j minus 2k. That will be your vector C. You see? Imagine in 2 dimensions is super easy. So this is the basic theory to how to add vectors with numbers instead of with rulers. We're going to practice this in class, and this will be the end of the video.